The output from the IC, there at pins 12 and 13, then drives to the right into a push-pull amplifier composed of Q879 and Q881. Now the horizontal or X portion of the readout information drives single-ended into the base of Q879, and that transistor in Q881 forms a paraphase amplifier for that readout information. The output then, push-pull, drives into the right and left deflection plate amplifiers. Let's take the right one up at the top there. Goes into first an operational amplifier composed of Q887 and Q889. That in turn drives into another operational amplifier composed of everything else off to the right. Then down in the lower left-hand corner are the XY delay compensation networks. All right, let's go back over to the input with the 25 millivolts per division per side terminated in 50 ohms. The emitters for those input transistors come out at pins 1 and 16, down at the bottom of the IC, and 8 and 9. The output at pins 12 and 13 is terminated off to the right in 50 ohms. Now this is the older horizontal channel switch that was used in some of the earlier and slower instruments. There it had a gain of 1. Here, however, in order to get the linearity that we needed at the 500 picosecond sweep speed, they had to decrease the gain to 0.6. Now let's drop down to the lower left-hand corner of that IC, where at pin 4 we have the display B command, and as the name implies, when that's high we pass the output from the B generator, and when it's low we pass the A generator. Now just above that, pin 6 has the XY inhibit, and when that's high we don't pass anything here. That's during the time that we write the character, and the input is inserted, as I said a moment ago, into the base of Q879. Okay, let's take the minus output at pin 13. Goes off to the right where we see the 50 ohm load comprised of the parallel combination of R854 and R853, driving then into the base of Q879, and a like network, of course, on the other side. Now in between the two signal paths is Q859, which is used as a readout center adjustment, but only when the readout is being written on screen. You'll notice that the XY inhibit comes in at the base of that transistor, which turns it on, and the current flows through the transistor into the arm of the readout center control, R857. Well, just up above is the X signal input when we're writing a character. Notice the selected resistor, R850. I said a moment ago that the gain of U825, the horizontal channel switch, was set at about 0.6. However, we have no real control of that gain, and it will vary IC to IC. Well, over in the emitters of the push-pull stage, Q879 and Q881, we have a gain control which can compensate for the gain differences in the horizontal channel switch, and then, of course, the inherent gain of the entire amplifier, as well as the deflection sensitivity. However, in order to match the readout to the other display, we need that selected resistor, R850. All right, that information then, as I said earlier, becomes push-pull in paraphase amplifier Q879 and Q881. Now the emitter tail for that stage flows in through R869 and then up to the top of the page to plus 15 volts. However, when we push the beam finder button, that path opens and we go through an additional 5.6K value of R868 to plus 15 volts, thereby reducing the current and reducing the scan. Now that would also reduce the standing current drive to the output amplifiers, so that current is inserted then with the beam finder switch into R886 and R896, so that there's no significant change in the standing current in the output amplifiers when we've pushed the beam finder button. Now the output from, say, Q879 looks into an operational amplifier, so Ri for that op amp would be the emitter tying resistors between Q879 and Q881, and that's where we've placed the gain adjust, as I mentioned a moment ago. R876 and C876 provide some high-frequency compensation to compensate for losses within this amplifier. R878 and the network on the other side are thermal balance resistors, bypassed as usual by C877. Now notice that those resistors are of a different value, and the reason is that Q879 is looking into a NPN, and down below Q881 looks into a PNP, so there's a 1.4 volt difference. So the thermal balance resistors as well as the collector load resistors are a different value. Notice that the collector of Q881 returns to a minus 50 volts instead of a minus 15, as does Q879. Right off the base of Q881 is network R865, CR865, and R864. That network has a negative temperature coefficient and compensates for a drift, which is accumulative throughout the amplifier. Okay, let's look at the right input operational amplifier composed of Q887 and Q889. Q887 is collector loaded stage driving into emitter follower Q889. The emitter follower provides a low impedance drive into the output operational amplifier. RF is R885, and RI would be one half of the emitter tying resistors between Q879 and Q881. Well, let's get the signal polarities straight. In at the base of Q879 we had a negative going ramp. At the collector would be positive going. Now I realize that that's a low impedance null point there, and there wouldn't be much signal voltage, but we're just trying to keep track of polarities, that's all. Now at the end of retrace, when the beam is clear to the left of the screen, then Q922, way over to the right in the output right amplifier, would tend to saturate. We'll look at that later. But before that happens, Q887 collector will have moved up to the point that it will lift through VR884, lift the anode of CR883, and turn that diode on. All right, we've got a feedback path now of effectively 100 ohms, which just stops the gain of that amplifier and limits the output excursion such that Q922 doesn't saturate. R883 there is just provides keep alive current for the zener. Let's see, CR887 is a Shockley diode, not Shockley. I understand it has about a 400 millivolt junction drop, and the purpose there is to keep Q887 from saturating. Keeps that collector from going more than about 300 or 400 millivolts below its base. CR889 off the emitter of Q889 provides some temperature compensation. CR888 provides base emitter breakdown protection for Q889 during retrace time. Now we'll get back to that diode and that current path a little bit later. All right, so we have a negative going ramp at the emitter of Q889 when it drives into parallel PNP transistors Q901 and Q902. Now at the 500 picosecond sweep speed, we pull about 80 mils through those transistors. Now at the time this instrument was designed, we couldn't buy a single PNP transistor that could quite hack it in this configuration, so they just placed two transistors in parallel. All right, the output from that parallel emitter follower and drives into a slow operational amplifier. Ri is R929. We then go through collector loaded stage, Q925, in through current path, grounded base amplifier, Q922, to the right-hand deflection plates. RF, of course, is R926. Now, RL, the collector load for Q922, is, in addition to the feedback path, the constant current supply furnished by Q912. Notice the fixed voltage on the base. The constant current, then, is supplied by emitter resistor R913. Now, notice that the feedback resistor is compensated by C926. Ri, on the other hand, is compensated by C928, but has a 1K resistor in series with it, which slows down the response of this so-called slow feedback amplifier. Now, the fast path is from the collector of Q901, Q902, in through C912, through Q912, to the right-hand deflection plate. Now, let's see how that works. Now, we said we had a negative going ramp at the bases of Q901, Q902, returning those transistors on hard. The required current comes out of those capacitors down below, C905, C906. Now, it can't come out of the slow operational amplifier because of the delay through that 1K resistor in series with C928. All right, as Q901 and Q902 turn on hard, the current then flows through the collectors, those transistors, through C912, through Q912 to the right-hand deflection plate. I guess I turned things around and used conventional current there for the moment, didn't I? Well, at any rate, the feedback path takes off from the right-hand deflection plate, feeds back to the base of Q925, holding it constant at very fast sweep speeds, or the start of the fast sweep speeds. And as the design engineer said, the slow amplifier thinks it's been doing all the work, simply because it operates in the normal manner, having been aided by the fast path through Q912. Now, during the time that the ramp was being formed, as I said a moment ago, current is pulled out of capacitors C905, C906, kind of down in the middle of things there. Now, during retrace, those capacitors have to discharge so that they're all ready to be used for the next cycle. And the discharge path gets a little difficult because Q889 is going to disconnect, as will Q901 and Q902. Now, we're talking about the very fast sweep speeds, of course. All right, retrace will lift the base of Q889, turn that transistor off, then CR888 will take over. Well, that lifts the bases of Q901, Q902, turning them off. CR902 turns on. And now the discharge path for C905, C906 is up through CR902, to the left there, through CR888, and up through R887. Now, there's going to be some discharge path up above through R905 also. Well, let's look at the left deflection plate amplifiers. Really a mirror image of the right deflection plate, except that you'll notice that driving into the output left amplifier, Q909, is a single transistor. They were able to buy an NPN which could handle the current. Everything else appears to be just about the same. Now, we've used NPNs instead of PNPs and PNPs instead of NPNs, such that as the negative going ramp appears at the base of Q897 down below, that turns that transistor on, We then have a positive going ramp at the base of Q899, which turns that transistor on. That in turn turns on Q909, and you see we're increasing current in each case as the ramp is being formed. Now at the very fastest sweep speeds, as the ramp is forming and we're charging the horizontal deflection plate capacitance, there's a complete current loop. Let's begin with the left deflection plate, pass through Q942, through C943, Q909, out that emitter, through C905, C906, in through the parallel combination of Q902, Q901, out that collector, off to the right through C912, Q912 to the right-hand deflection plate. The path then is completed through the capacitance of the right, then the left deflection plates. C905 is adjusted at the 500 picosecond sweep speed. R906 is a damping adjustment to suppress a tendency for this circuit to ring a bit with lead inductance. I should have called your attention earlier to the gain of the output amplifiers. It's quite obviously 10. RF is 99.9K and RI 4.99K. Well, that brings us to the XY delay compensation network. The circuitry is found in the lower left-hand corner of this page. In XY operation, we need to delay the horizontal signal as much as the vertical is delayed in the delay line. These networks are optional. They're located on a card, and the card includes two delay networks, one for channel A and one for channel B. Once they're installed, they're connected automatically whenever you select XY operation. That position is usually labeled amplifier in the 7000 series time-based plug-ins. Now there's a relay that connects these compensating networks into the circuit. Now it's possible to alternate or chop between channel A and channel B, one of which is in conventional time mode and the other can be in XY mode. Now with this phase correcting network, the external horizontal has a band pass of 1 megahertz, adjustable to within 2 degrees. Now on schematic 7, look just above the delay compensation network, and you'll notice the blue overlay where it says A19 horizontal interconnect. Well, if you'll just pull that section right out of there, that's where the delay compensation networks plugs in. Now these two networks are identical. We'll talk about the top one. First to the left is the relay, and in the position shown, that's for time-based operation. The output from the time-based plug-in just passes right on through to the horizontal channel switch. Now in XY mode, when the relay closes, then the compensating network is connected. Now when the relays are turned off, the diode CR801 gets rid of the current from the inductive kick. Now a thorough analysis of this lattice network is a little beyond the scope of this tape. However, if you'd like some additional reference, I would suggest that you look up the book Network Analysis by M.E. Van Valkenburg. It's a Prentice Hall book. Or if you'll write to R. Michael Johnson in the engineering department at Tech, he has the paper that he used for his master's thesis explaining this lattice network. Now notice that the network is terminated in 50 ohms at the input to U825. Now we can say these things about the delay network. One, if you choose the components properly and terminate it properly, it will exhibit a flat band pass with a constant input impedance at all frequencies up to 2 megahertz or so. In this case, that impedance is 50 ohms per side. 100 ohms side to side. It has a constant delay up to that 2 megahertz. Now, looking into the lattice network, it appears as a simple R of 50 ohms in parallel with 1/2 of C803 and C804. Now, in series with that network is the L over R, composed of R802 and L802. Now, that can be redrawn to form a simple divider network. The top of the divider is composed of R802 and L802. The bottom would be 1/2 of C803, C804. Now, that series network would be in shunt with a 50 ohm equivalent resistance of the lattice network. Now, that's not a compensated divider, not at all frequencies anyway. As X sub C goes up, then X sub L would go down. However, looking into the divider network, that is clear across it, we see a constant impedance at all frequencies. Notice that the C that appears across the bottom of the divider is adjustable, and that provides the variable delay. It's used to match the delay to that of the vertical to within 2 degrees at 1 megahertz. The adjustment has a range of about 10% of the total delay of the network. The vertical delay is 66 nanoseconds. There's a slight difference in signal loss across the network as the adjustment is made. But if you make that adjustment first, it can be compensated for by the gain adjustment in the plug-in that you're using. Well, let's turn next to the CRT circuit. Let's pull out schematic 11. It also includes the Z-axis circuitry. Just a brief look at the CRT first. Notice that the accelerating anode has 21 kV on it, and the cathode a minus 3 kV, so that's 24 kV of accelerating potential. Right up at the top center of the page, with Q1627, Q1631, and U1635 is the regulator circuit. Just below and to the left is the dynamic focus circuitry, composed of U1745, Q1755, Q1757, 1765, and 1769. Then down below center, all the rest of the transistors there have to do with the Z-axis circuit. Now, the output from the Z-axis drives into a DC restorer supply, which provides the CRT grid bias. The output from the dynamic focus circuit goes into another DC restorer, which supplies the focus anode voltage. Let's begin in the lower left-hand corner where the Z-axis information comes in. The Z-axis input comes from the logic circuit. It varies from 0 mils to 4.25 mils. Now, that varies the output from this Z-axis circuit from 0 volts to 60 volts. That becomes the drive to the CRT for unblanking. Then the readout is a similar current which comes from the readout circuitry. All right, that passes into the emitter of grounded base amplifier Q1805, and from there into an operational amplifier. Now, that's a non-inverting op-amp in which the plus input is the base of Q1808 and the minus input is the emitter of that transistor. You see we have double polarity reversal through Q1808 and through Q1824. The output from the circuit there at the collector of Q1824 passes through emitter follower Q1827, and that's the output from this op-amp. RF is connected to the collector of Q1824. It's R1824. Now, the gain of this amplifier is 1 plus RF over RA. We've already pointed out RF, and RA is everything looking from the emitter of Q1808. In other words, it would be the equivalent of R1808, R1809, R1810, and that in parallel with R1814 to the emitter of Q1815. Now, the gain expression, you remember, included RA, and we're going to vary RA with the Z-axis amplifier gain adjust. Now, the bottom of the RA resistor, instead of going directly to ground, as I said, goes to the emitter of Q1815, and we can move that up and down with the output level control, which changes not the gain, but the level at the emitter of Q1827. Now, before we leave this little amplifier, C1820, right off the base of Q1824, just a speed-up capacitor. CR1822 protects the base emitter junction of Q1824 in case Q1808 is pulled out of the socket when the instrument is hot. Okay, the output amplifier is another operational amplifier with a slow path and a fast path. Let's take the slow one first. The operational amplifier consists of R1871, the RI value, Q1874, and Q1876 in a cascode configuration. RF, therefore, is R1873. And the collector of Q1876 is the output from the circuit. RL, for the operational amplifier, is the constant current supply, Q1854. Notice that the base is set at a fixed voltage, so the current through emitter resistor R1854 will be a constant. Therefore, we have a constant current collector supply for Q1876. Now, the fast path is up through parallel PNP transistors, Q1834 and Q1836. Now, we're going to draw enough current at the very fastest sweep speeds so that a single transistor can't take care of all of the current. That is a single PNP. The emitters are long-tailed into constant current supply, Q1838. Notice the fixed voltage on the base and the constant current through emitter resistor, R1838. Now, for fast information, those emitters are bypassed by C1842, C1841, and then with a large signal, if the emitters begin to move, and CR1844 or CR1845 come into conduction, adding C1844 and C1846 into the circuit. Now, that shapes the response of Q1834 and Q1836 that weren't exactly linear. Now, I understand the circuit is to be modded, in which more linear transistors will be used, and the diode shaping circuit then will be removed. The collector supply for Q1836, Q1834 is a Thevenin equivalent of R1832 and R1831. Okay, the fast unblanking information is capacitively coupled through C1850 into the emitter of Q1854. Now, the output from that fast circuit, of course, is tied to the same place as the output from the slower circuit. In other words, we have common collectors there at Q1854 and Q1876. Now, the output from the fast amplifier